Yeah. Hello, everyone. Let me start by thanking the organization of OHBM for providing me this wonderful opportunity to present this study on the resting state oscillatory correlates of speech and noise recognition. I'm sure all of you experience conversing in noisy environments on a very regular basis, such as it happened recently when you visited the center of Rome, or when you took the public transportation, or at the welcoming party, the welcoming reception on Sunday. And I'm pretty sure you were able to successfully have these conversations in spite of very high noise level. And indeed, the ability of the brain to recognize speech in very high noise level is a very remarkable ability. However, people differ quite dramatically in terms of the level at which noise induces breakdown of intelligibility. So in this study, we aimed at testing whether we could predict such individual differences from resting state MEG data. In order to do so, we analyzed the data from 89 young and healthy participants made available as part of the Human Connectome project, who underwent MEG recordings, followed 1 or 2 days later by a speech and noise recognition task. And I'm now going to spend a few words on this task, which is called the word in noise test. And as the name suggests, participants are asked to listen to and orally reproduce isolated monosyllabic words embedded in multi-talker bubble. And hopefully now you will be able to hear 2 samples.
Say the word youth. Youth. Say the word cool. Cool.
So what you just heard are the easiest trials. However, noise level increased throughout the task, and therefore the signal-to-noise ratio decreases. The word in noise test assesses the word in noise test score represents the lowest signal-to-noise ratio at which participants are still able to correctly recognize the word, and therefore a low score represents high resilience to noise, so good performance. And all of our participants of our sample all were within the normal range. However, their performance was relatively heterogeneous, as expected. And this is because word in noise recognition, speech in noise recognition, is associated with a number of low-level and high-level cognitive factors that we wanted to remove from our analysis. And in order to do so, we exploited the wide range of subject measures that were part of the Human Connectome project assessment, which include demographic information, a number of tests of cognitive ability, emotionality, perception, motion, a number of questionnaire, etc. We selected those that met some criteria that we took from that were established before, that basically those variables that were suitable for our further analytical purposes. We ended up with 132 subject measures, and here you can see the correlation coefficient between each of these and our variable of interest, which is the word in noise score. We found both significant negative correlations with word in noise signal-to-noise ratio, which represents a positive correlation with resilience to noise. And accidentally, we found a number of executive functions, working memory, and a measure of fine and timely motor movement, positively predicting resilience to noise. On the other hand, a number of measures of tobacco consumptions were negatively associated with resilience to noise, and this is trivially explained by the fact that smoking is associated with hearing loss. We regressed out variance from each of these variables, even those that were not independently significantly associated with our variable of interest, since they are sources of individual differences which we wanted to remove. In order to avoid overfitting in the regression model, we used a principal component analysis reduction approach, whereby we collapsed the variance in this set of predictors into a number of principal components. We selected the first 25, explaining 80% of the variance in the original set, and we regressed this out from our wording noise score. In gray, you can see the correlations after the confounding procedure, as well as how the wording noise scores changed. I'm now going to spend a few words in explaining how the MEG data were acquired and analyzed. So participants laid supine, such as in the image, in a darkened room. Data were acquired in 3 runs of approximately 6 minutes each. And after artifact removal, we were left with about 15 minutes of utilizable recordings per participant. We calculated the power spectrum density in source reconstructed space at each source point of the time series standardized over time from 1 to 40 hertz in 1 hertz bins. And we subsequently used the k-means to cluster these 40 narrow bins into 6 wider frequency bands in order to reduce dimensionality. And we correlated voxel-wise power at each of these 6 frequencies with the speech in noise recognition test score. We found significant associations in 2 neighboring frequency bands, one between 21 and 29 hertz, the high beta band, and one between 30 and 40 hertz. In both frequency bands, higher resting state power was predictive of a better, of higher resilience to noise. In the low gamma band, we found small clusters of relatively small clusters of associations, peaking in the right posterior superior temporal gyrus. However, the largest and most significant cluster of association was found in the left hemisphere, in the high beta band, spanning the inferior frontal gyrus to the temporoparietal junction and peaking in the left posterior superior temporal gyrus. We speculate that these effects reflect the neural correlates, the oscillatory resting correlates of the processing of phonemes. This is because our results are very much in line with processing at this level of analysis, both spectrally and spatially. Indeed, spectrally, a number of electrophysiological studies have shown that activity within this region between 20 and 50 hertz, more or less, is associated with processing of phonetic features and their phonological labeling. And recently, there is even some causal evidence from non-invasive brain stimulation, and indeed 40 hertz TACS over auditory cortices impacts phoneme labeling. And also especially the posterior superior temporal gyrus, as highlighted before by the speakers before me, and especially the left posterior superior temporal gyrus has been shown by a number of fMRI studies to be the locus of categorical perception, where phonetic features, rapid phonetic features are categorized into invariant and symbolic phoneme units. And there is also evidence from intracranial recordings in humans for this. So to wrap up, we were able to show that we could predict speech in noise recognition performance from resting state data. We regressed out a number of unspecific contributors in order to assess the perceptual processing associated with speech in noise recognition. We found that higher power, in particular between 21 and 29 hertz, peaking in the left posterior superior temporal gyrus, was predictive of resilience to noise. And I want to conclude by saying that this study provides support for the idea that there may be such a thing as an optimal resting state level of activity for phoneme processing, maybe for other processes as well. And if you would like to find out more about this study, I will be at the poster session this afternoon. And I also want to thank the Swiss National Science Foundation for funding the project, the Human Connectome project for providing the data, and of course my supervisor, Professor Hervé Adelman, as well as Dr. Becker for making this possible, and of course all of you for having the patience to listen to me. Thank you.